Hello and welcome. So here I am today going to try and explain as clearly and easily as I can how the support vector algorithms can work. And with that explanation, I'm also going to give you all the code that I used here to make these charts and make these graphs, and just basically explain how that works, how to produce the thing that we have here. So the core idea behind the support vector machine is that we're actually dealing with an equation of a plane in this two-dimensional example at least. You can go up to higher dimensions and things just naturally extend. You do lose the geometric interpretation if you go beyond 3 dimensions. But here we are in 2 dimensions with 2-dimensional data, but we end up with an equation of a plane in 3 dimensions. And you might be looking here and thinking like, hey, how on earth do we get an equation of a plane when our data is 2-dimensional? Well, here we go. Oh, excuse me. So the core idea is we have data up here, which is one particular class, and we have data down here, which is of an alternative class. So one of these data sets, we're going to assign a positive class and then a negative class. And then what that means is that with each data point assigned to each of these classes, they're either going to have a +1 or a -1 assigned to them. So now we want to divide this data by, we can call this a street. Kind of looks like a street. That is, sorry, there's something in my throat. That is as wide as possible. Okay, as wide as possible. So we basically want these lines, right, that are going to be as close to these data points as possible, that are perpendicular to each other, such that the distance between these two lines is as long as possible. Okie doke. So that's what we want. Now the question is, how on earth do we get there? How on earth do we get there indeed? Okay, so let's head towards the equations and how we derive them. Okay, so in case you're wondering, this is the equation of our plane up here, right? This line here is often referred to as the support vector. And when you set z equals to 1 in this equation up over here, this is going to produce this line. Similarly, when z is set to 0, this equation of this plane reduces to this line, and for z equals -1 as well. So if you take a z value, right, in a plane, and you set it to any kind of number, whatever, what have you, you reduce that plane into a line. And that's how this plane and these lines are connected to each other. These lines all lie on this plane. Okay, let's head to the derivation. Okay, got to do a rotate. Here we go. Okay, here we go. Let's zoom in here. Okay. So this is my neat drawing of what we're talking about. So we have the streets here, okay? These are support vectors, z equals 1 and z equals -1. These are positive data up here, designated by plus signs. And these are negative data down here, designated by negative signs. And going back to our plane example, if this is z equals 1 and that's z equals -1, in this area here of the chart, this is in this area z is greater than equal to 1. So if you put an x and y value in the equation that I had earlier, you would achieve a z value greater than 1. Similarly, in this area below the z equals -1 support vector, if you put in these x and y values into the equation, you'll get a z value less than -1. So when we are deriving our algorithm, one of the things we're looking for is we want these data points. Yes, we want these data points. Ideally, we want them on the line z equals 1, but we'll settle for as close as possible to z equals 1. So it's these equations of these lines that we want, and it turns out we actually just need the equation of one of these lines. So just for some notation, our data points, I'm designating as xi, and they have an x and y component. If you're familiar with other machine language nomenclature, often you can refer to these as feature 1 and feature 2. W is our vector that is perpendicular to our street, and this is also a vector that's going to be perpendicular to the plane, if you can think of it quite like that, except the plane would be 3-dimensional vectors. But these lines, also this W is going to be perpendicular to the lines of a street. yi, as I mentioned earlier, is going to be applied to our class. So each data point, okay, is going to be of a positive or a negative class. We have to have this information. So yi is either -1 or +1. Okay, this is an obvious mistake in my writing here. Yi can either be -1 or yi can be +1. Okay. Okay. So for the positive data, yi is +1, and for the negative data, yi is -1. So I'm writing out the generic equation of a plane in this form. It's basically just a rearrangement of equation of a plane. You could have a coefficient in front of z. It's not necessary because you've got scalars in front of everyone, so you can just drop one of the scalars, one of the coefficients if you want to, and then everything else will change accordingly. So that's fine so far. So for the line z equals 1, okay, we set z equals 1, so our equation of our plane reduces to this, okay? Now this is an equation of a line. Another way of writing this out, okay, we've got wo and w1 and x and y. We can write this out as xi.w plus b equals 1. And if you look at other explanations on how support vector machines work, they'll probably just jump to this equation here or some form of this equation here. But there is a geometric interpretation to how we got this based on how an equation of the plane works and how we generate our support vectors. So our decision boundary, okay, let's just think of the positive points first. Our decision boundary is going to be based on xi.w plus b must be greater than 1. You could do equals to, you're going to get to the same place. It's not really important, but if you wanted to, you could put an equals there too, that's fine. So this is our decision boundary. What we're basically saying is all our data points, okay, all our data points on the positive side has to be greater than equal to 1, which basically means that their z component has to be greater than 1. Okay, that's great. That constrains our positive values, but we also need to constrain our negative values as well. So that's one decision boundary. So our negative values, right, are going to need to have a z value less than -1. Less than -1. And it turns out, right, if you multiply a value, a negative value, -4, what have you, by -1, you will get a positive number greater than 1. So that's kind of how this works. We multiply our positive data by yi, which is 1, doesn't change it, and we're going to multiply our negative data by yi, which is going to be -1, which is going to change it to a positive value greater than 1. So it's kind of a neat way of rewriting this, because now this decision boundary equation is going to work for both our positive values and our negative values. For our negative values, for our positive values, it's not going to change anything because yi is 1. For our negative values, this is going to be a negative number, right? And we multiply the negative number by -1, and we're going to end up with a positive number that is required to be greater than 1. And if it wasn't greater than 1, then it would fall into this error here, which we don't want, so it'd be rejected. So this is basically the crux of it. Okay, this is our primary decision-making equation, and it's actually remarkably simply written. Now that I look at it again, and that's what we have. This is how we're gonna do it. But one thing that needs to be mentioned is we're not quite there yet, because there are going to be very, very, very many planes that will divide this data in the manner in which you want to divide it. So we've just, that algorithm is just going to find those planes which will segregate this data correctly. But remember, we want the equation that segregates data with the street of maximum width. So we want this perpendicular distance to be as great as possible. And to do that, we're going to need to think a little bit about how scalar projections work, right? We all remember our friend scalar projections. Let's have these things alongside. Okay, so I haven't drawn it here, but imagine we have imagine we have 2 points, right, on the line as the objective. So we want one data point on this line, and we want another data point on this line. And then we can take, and that's basically going to be our A. Our A is going to be the vector that connects this line to this line. Any vector, right? It's not important. And then we want the scalar projection or the shadow cast by that vector on W, right? Because that's going to give you the projection of this line on W, and that will give us the width of the street. Okay, so the projection of A, right, on B will give us this curly thingy over here, which is going to be the width of our street, and that is given by this equation here, A dot B divided by the magnitude of B. Now, the neat thing about this is we don't actually care what the projection is, okay, and nor is A actually relevant. A can be any vector that connects those two lines, and we don't actually care how wide the street actually is. We just want the street to be as wide as possible, and for the street to be as wide as possible, we need B, the length of B, to be as small as possible. So of all the planes that will divide the data correctly, we're going to choose that plane with the smallest W, the smallest length W. And that's it, right? Once you found the equations that divide the data correctly, we're going to pick the one with the smallest length W, and that is going to give us the equation of the plane that will divide the data correctly, and that'll be our answer. Okay, so let's do it. So this is a script, right, that will do that for us. And I'm going to talk through the script a little bit, how it's all going to work. So we do need to generate some random data, some random numbers. And so this is the equation here that's going to generate a random data. And you can change this and modify this as much as you want. We've got a number of samples here, and we've got the random state here. So you change the random state, you can end up with different data, and that's fine. Okay, let me just remember how this all works. This is going to assign -1 or +1 to our data, depending on what its characteristics are. So what we're trying to find is 2 clusters of data with different classes. Okay, and then once we have our data, this is our learning rate, and this is the range that we're going to search for. So we're actually going to iterate. So we've got 3 coefficients which we need to find. We've got this W0 coefficient, this W1 coefficient, and B. So there are 3 constants that we need to find that will generate our equation. So how we're going to do this is we're actually just going to iterate. We're going to iterate through WO, and then in another for loop, we're going to iterate through W1, and then in another for loop, we're going to iterate for B. And then we're going to find all the solutions that divide the data correctly, and then we're going to pick the one with the smallest W, and that'll give us our most optimal solution. So here it is. We're going to just start with some arbitrary starting value for W, okay? And then we're going to search between -1 and 1 with the learning rate as we defined up here. And that's the one for loop, and this is the next for loop for W1, and this is the for loop for B. And then we're going to go through this, and here is the first decision equation I was describing. Okay, it's a dot product of the W vector with the X data vector plus B times Yi, and the way we've done this is that if the Z value for this equation is less than 1, it's going to be false, right? So that means if the data point lies below this line, or in this area, in this region, we're going to classify that data point as false, and then this is not going to be a solution for our problem, and then we're just going to break up the for loops and start again. Okay, if all data points are correctly classified, we're going to remember them. More than that, we can also calculate the length of W. So this is a for loop that basically iterates through all the different coefficients for planes that could solve our equation, and if it does, then we're going to store W, And then basically we're just going to, so yeah, norms is the sorted list by the length of the W vector. And then our minimum W length is the smallest one of that. And here we actually get our W and B. This is our W, and that's going to be W0 and W1. And this is our B, right? So this are our final coefficient solutions. There is a possibility that there is no solution. Okay, if the data points lie along each other or no line can divide the data correctly, it's very possible that there is no solution, and this section of code deals with that potentiality and then it plots it. Okay, and the rest of this equation, everything here is just plotting protocols. So the crux of it is this is the first decision, decision boundary, checking if the plane does divide the data correctly. And then this calculates and stores the coefficients which do divide the plane correctly and the length. And here we just select basically the plane with the smallest length. Wunderbar. Okie doke. So let me run that code and show you that it works. Depending on the learning rates that you choose, it can take a little time to run. If you do decrease the learning rate, the code will run much quicker. And here we are. And this is the same. This is just a saved JPEG of this guy here. So I'll close this away. And you can see that the data points look like they do lie very close to it. But if you zoom in, you will see that they, in fact, don't lie on it. There we go. Another fun thing that I do want to point out is, okay, notice how the top line here is z equals 1. Okay, the top line is z equals 1. So what I'm going to do here is I'm going to do something a little sneaky, and let's make sure I get it the right way around. Okay, so we want to reject it if it's less than 1. Okay, but what if I go greater than -1 and save that? That's the only change I'm making here. Greater than -1. So if it's greater than -1, it should be false. I'm going to run the code. And hopefully it's going to work correctly. It should do. Ha! And now the code has worked correctly. And you'll see that we actually get a very similar solution, but slightly different. Before, this top line was z equals 1, but now it's z equals -1. And the difference is that I based the equation, the decision equation, on this negative support vector rather than up here. And you can do it either way, it doesn't really matter. But what this has done is, and what does show is that there are actually two solutions to this problem. One is a plane that slopes upwards towards Z1, and the other is a plane that slopes from this point up to here. So you just got different sloping planes. The only difference is that the coefficients are just, you multiply all the coefficients by -1 to go from the one plane to the other. So there are actually two solutions to this problem. I think that's pretty cool and quite neat and quite fun to point out. So let's change that back to, if it's less than 1, it's false. If it's less than 1, it's false. That's right. Gotta get things right in your mind. And let's just change this to a different number, and then you should see how this code works on different randomly given data, and it should work. With a bit of luck, please work. And here we go. It's worked again. This time the support vector, the negative support vector is up here. And what this just means is that it means that this was the negative class, or this is a positive class, or they swapped around. And that will help determine which of these lines end up going to be the negative support vector and which is going to be the positive support vector. And this data point actually lies very, very close to the line. And as you decrease the learning rate more and more and more and more, these data points are going to get closer and closer to this line, and you're going to end up with a better and better solution. So I think that's everything that came here and I wanted to say. I hope you found this helpful. If you did find this helpful, please let me know. When I was trying to learn how support vector machines worked, I don't think anyone actually gave this kind of geometric interpretation to how this plane works and how the decision vector, this decision boundary equation, like relates exactly on that the equation of the plane. So I hope you did find this helpful. This was a very simple example for how support vector machines work. These problems can get much more complicated. One complication that I will point out now is that often there is no solution, right? Just because the data is clustered upon each other. But what you can do, and what any generic algorithm should do, is apply an array of transformations. So you can transform your data somewhat into a different kind of nature, and then if you couldn't solve the initial data correctly, you then possibly can solve the transformation correctly. So ideally you would perform an array of transformations, and then you apply the code on the transformed data, and then from there you can select your best solution. And that's particularly helpful if you do have overlapping data or data that can't be easily or singularly segregated by lines or planes. And you can also, this doesn't only work on two-dimensional data, this can work on n-dimensional data, but you do completely lose this kind of geometric interpretation, but everything else just extends. So it does work. So once again, I hope you found this helpful, and if you did find it helpful, please let me know, and that'd be great. Thanks for watching.